So yes, we'll be talking today around networks and how they're inherently insecure, fundamentally because networks are designed to share information and not to do other things. Obviously, IoT is built around connecting devices and the network connectivity to them, and therefore, how do we protect inherently insecure in order to protect the data, the devices, and the organization? So, first of all, a little bit of an introduction. Every organization is going through some sort of digital transformation, whether it is transitioning from a traditional hardware company into one that primarily develops software, to other companies who are just using digital tools and data in order to get more value from their organization and business outcomes. Fundamentally, though, achieving business agility and ability to develop new, better products quicker is a key part of this. And IoT is one of those outcomes of becoming a more digital, agile organization. So businesses are trying to develop these capabilities. But fundamentally, the biggest thing holding back IoT, the 2016 McKinsey report, it's security and the cybersecurity challenges that we have around that. Lack of standardization is the second one, which, as we've been talking today, is a lot around security and other things. So we know that's a problem. And we know organizations are currently seeing it as more of a problem. You speak to a CISO or someone within a security organization, it's things that they are spending most of their time on. It's, it's cloud, number one, maybe, and security, number two. And the reason for this is that we've had a lot of recent high-profile events which have caused people to really assess whether it's safe to connect things. One of them was, I think, 2015 or 2016, where people in the US got onto a local LTE 3G, 4G network, were able to get down to a specific vehicle, hack it, and take over controlling that vehicle while someone was in it, taking over, fundamentally getting into the CAN bus via the entertainment system or infotainment system. So, again, that's a network which is nominally private but fundamentally insecure. In 2016, there was a German steel mill which melted down because people got access to the SCADA systems. They were able to stop the local operators from shutting functions down, and the steel mill melted. It was like a multi-billion-dollar write-off of assets, which, again, shouldn't be happening. Recently, the Ukrainian power grid got hacked and was taken offline for a large amount of time. Again, critical infrastructure items in the OT world that really shouldn't be attacked and shouldn't have this avenue in order to get into them. At the beginning of this year, there was an attack in Saudi Arabia where people got into their systems at I think it was a chemical plant, and this system was meant to be airlocked, and there was no way into it, no way to hack it. But nonetheless, they did hack it, they did get into it, and they executed code on it. And if the code had executed, it would have caused an explosion and people would have died, and it would have been like the first national incident of people dying from IoT. There was a bug in their code, it wouldn't execute. Did they put it there purposefully to send a message, or was it a mistake? I don't know, personally, but it shows how we are getting to and how we've got to the point where now we're integrating IT to critical OT systems in the real world where deadly outcomes can occur if we don't manage security properly. I was recently speaking to a very opinionated blogger in the network world, and his opinion is that security doesn't matter. If you look at things like Target, you look at things like Equifax, they have recovered to the point that it hasn't caused them an existential business problem. Now, personally, I believe you could put up many reasons of where they've lost market value, maybe not done as well as the stock market in general, to build a business case around that. But that's the consumer side where people aren't going to die from it. If we look at the industrial side, the healthcare side, this is where it becomes fundamentally more important because we're talking about people's lives. Not on here, but recently, Wipro released their State of Security 2018 report, and their top-line figure that I pulled out of it is that healthcare is now the most attacked industry, with around 41% of attacks, twice the amount of finance, to which you think, well, why is that? because healthcare data is more valuable than financial data, because you can more easily build up a view of what someone is trying to do, what their habits are, to essentially spoof them and do financial transactions because you've got better data on them. And the biggest driver, they said, for this increase in attacks is IoT devices. On average, a hospital has 40 to 80,000 exposed endpoints, which are public internet facing. A mind-boggling amount that you need to grapple with. So then we get to the area where I'm really focused on, which is the agility and security that we need for IoT, for the digital transformation in general. It's not possible to achieve with a traditional network because it tends to be based upon static hardware, it tends to be based upon perimeter-based models. Instead, we need to create network capability which is abstracted from the underlying infrastructure, which allows us to connect these distributed applications in IoT, etc., and to ensure that we secure them. And, up and down, need to remember what I was told at the beginning. Looking a bit closer at that German steel mill, how that was got into, I think, is a perfect demonstration of what I'm trying to get to. They exploited human weakness. They did a focused phishing campaign in order to exploit someone and for them via email to bring something into their work network. They were then able to jump or hop from that work network and go deeper into the industrial network that they had on that site. Once they were in that industrial site, by hopping between those different zones, they were able to attack the industrial control components, which were not designed for TCP/IP. They were not designed for the internet-connected world, and they were able to prevent the blast furnace being shut down. Looking at the analysis of why this occurred, they could only assume that there was either an insider executing it or there was insider knowledge, because they had such an advanced technical understanding of both the IT systems and the OT systems. So whether it was someone malicious who had been fired, or someone that just wanted to cause damage, or some other reason, we can only assume that there was some insider involvement. And this is fundamentally why perimeters don't work and we need zero trust. And a little bit of an overview, because I learned recently at IoT Solutions World Congress, I assumed everyone knew what zero trust was. And then when I asked people, 90% of people didn't. In 2012, Forrester released a set of white papers and positioning papers where they said the perimeter-based model of security is defunct. And it's defunct because of two reasons. One, we're distributing applications everywhere with IoT, SaaS, multi-cloud. Therefore, we can't just build a perimeter and protect from the external world. And at the same time, more than 50% of our attacks come from internal to the organization, and building a perimeter doesn't protect you against that. So instead, we need to move to a zero trust world, which says everything is guilty until proven innocent. And you predicate building up trust around multiple ways, whether it's hardware root trust or device trust or human passwords, biometric trust at the endpoint, so that someone can securely get access to the application from anywhere and not just being in a certain location. And then you utilize technologies such as microsegmentation of applications, connecting apps rather than sites. You utilize least privileged access, where you specifically have to be allowed to access something before you're even able to see the applications that exist. You have to authenticate into the system before you get access to the system and see any visibility or data flow, rather than get access and then see what you can find. All of which integrates seamlessly into an identity access management system, so it's seamless for the end user, because if we put up blockers to an end user, they'll ignore that approach. So we need to bring zero trust to IoT, in our opinion, in order to solve a decent amount of these implementation challenges that we have with IoT. And that then comes to the question of, well, how do we enable that? And how can we, in fact, go beyond zero trust? Because zero trust, there's 5 levels of security, from people finding scripts on the internet and having a laugh, up to level 4 of malicious internal actors who are trying to do damage, such as we saw in the German steel mill. Level 5 is state-level actors or people with concerted resources and want to attack your organization. Zero trust very much talks about level 1 to 4 and protecting you against those. It says nothing about that 5th one. So then we have to start asking the question, okay, how can we go beyond that and protect? If we're talking about critical infrastructure, if we're talking about industrial IoT, where there's much higher levels of security required, and we're looking at things like the Ukrainian attacks, Stuxnet, all the attacks we've seen recently, many of them look like they have state-level actors. And there's really a few ways that we can do this. So I'm going to specifically talk about how we do it at NetFoundry with our product. But I know there's other organizations that are looking to implement zero trust within the IT realm as well. The image I'm going to go through is on the left-hand side, we've got someone consuming an app. On the right-hand side, an app hosted. In the IoT world, it's either a smart device or some edge processing on a gateway, while you've got an application hosted in AWS or Azure, something like that. At the top, we've got the NetFoundry GUI interface and automation engine, where you say, I want to connect this app to that app, and it does all the complex network engineering for you. We've then got the middle block with the 4 arrows on, which is the network controller, which manages whether things should have access to the data plane. And then that lowest level of the 4 transfer nodes is your data plane, 3 active, 1 on standby. So there's 6 things that we do here. 1, we deploy as that zero trust network. That means regardless of whether you're on an internal network or an external network, you build an overlay on top of it. And the people have zero visibility of that until they've been authenticated into the network, until you've said, I know this person should have network access, I know they're trusted, and we have built up that trust for them to have access to application A. Therefore, I build that capability for them to connect into it. We can build that around multiple different ways. There's various vendors here that are talking around how we can do trust at the edge. For us, as much trust as possible, please. If you can get someone with a TPM and take trust from that, if you've got someone with ARM Trust Zone, you can take some trust from that. If you've got a Intel trusted execution environment, you can take trust from that. Various ways that you can build up that trust model to say, I know this is the unspoofable device, I know it's running software that's in secure boot and execution and therefore hasn't been tampered with. All of these ways allows us to build up more trust and say this is a trusted device and therefore it should have access to the network. The second thing that we do is we do that application level micro-segmentation. One person, when I explained NetFoundry to me, said, oh, you do NSX, the public internet. I was like, yeah, sort of. you have, rather than having site-to-site connectivity, you have application-specific. And each of those applications is independently isolated from one another. And where this becomes really interesting is in IoT, where we have a naturally heterogeneous landscape, where on a smart connected vehicle or in a smart building, you might have 4, 5, 6 different applications or pieces of hardware where people want to get data from that, where they want to access their specific application, and where you need to make sure they have their own virtual private network into their application on that endpoint. So in the smart building scenario, you can have a building owner, you can have a subtenant, you can have some system integrators, you can then have 6 vendors of HVAC, remote vending machines, various lighting systems. Each of them can have access to their system and only their system, so that you don't get a scenario such as which happened with Target, where the third-party building management system provider was hacked, then they jumped onto the Target HVAC, and then they jumped onto point-of-sale system. That should not be possible, and that's what we want to stop against. The third thing then is building around that least privileged access. So you have to explicitly be given access to an application and to say, you're allowed to access this if you build up the correct trust model, rather than getting access to a system and just saying, okay, which can I try to enter a password with until I can find some way to get into it. The fourth thing then is where we start going beyond zero trust. And that begins by deploying as what we call an invisible network. Fundamentally, you have a software-defined perimeter. It's work that originally started with Google and their Beyond Corp initiative, that builds around, well, as I'm abstracting layers and I've got a separated data plane and control plane, I can make sure that on the endpoint, I can make it invisible to the network it's connecting to. It's on the internet, but it's not exposed to the internet by doing a few things. 1, having IP address obfuscation so that it doesn't appear. 2, having only outbound connectivity and no inbound ports. And 3, then having a software that's on the endpoint which has just one rule, which is deny all traffic that's not been pre-authenticated come from a NetFoundry endpoint. That allows you, therefore, to, if someone somehow guesses your IP address and tries to DDoS it, the traffic's just dropped on the floor. It doesn't respond to it because it's dark until you have validated and authenticated trust into the network to the controller, and it says, okay, now we can build that outbound connectivity between things that should have connectivity on the data plane. The fifth thing that we do then by doing that is we're effectively abstracting the attack surface away from the enterprise into the NetFoundry data plane. And we do that, we protect that by deploying across different distributed sites in cloud environments with highly distributed, highly decomposable infrastructure, which you can spin up and down on demand as required, and then route between it, which effectively means there is no single middle or transfer node for an organization to attack. If they try to attack the data plane, you just move the traffic and you spin up new locations dynamically so that there's no one single point of failure. At the same time, the data transfer plane stores no keys, it stores no IP addresses, it stores no data. It's purely forwarding function, network virtualization forwarding function, in order to take away the value of anyone trying to attack your transfer plane. And then fifth, across that transfer plane, doing very AES 256 encryption, DB Helm exchange, etc. But then also having, because we're building multiple data transfer nodes in order to move the data across, we don't have one single middle because we can dynamically route across it. There's no single place that you can intercept because there's multiple and infinite amounts of places that could be exist at any one time. Almost quantum in terms of it's nowhere, so it's everywhere. At the same time, both that encryption and the path is all rotated either on a time basis, 5 minutes or 1 minute, or whatever the organization determines, while also being able to do it on suspicious activity, such as seeing things happening on the network. But it also gets you to the point where you can start saying, now I have a programmatic network on demand, what can I do if someone tries to attack my endpoint? If for example, someone comes into the building where your IoT device is, and to your southbound gateway they insert a device which doesn't have the correct cryptographic key, your gateway's going, oh, I'm not sure if this should have access. And the NetFoundry agent's going, this isn't a trusted endpoint that should be having its own app WAN into the endpoint. So then you could instead pretend it's having access, give it app WAN into some sort of honeypot, monitor its behavior, see what people are trying to do to your network in order to access it. Fundamentally, though, that gets us to the point where we were recently working with let's call them a global truck manufacturer, and they came to us and they said, we're building this connected truck for the future, and at the first it's just going to get data, but then we're going to move to truck as a service and all these really cool things that we can do with IoT. Fundamentally, we need to protect it because we need to protect our brand, and because we really care about safety, because we're in the OT real world. And they created this document of very deep threats of these are 7 things that we think could affect our organization that we need to protect against. And it went all the way from information disclosure to spoofing of the truck, cloud, the actual gateway endpoints, and down into denial of service and tampering. And working with various partners, we were able to show we can protect against all of these threats. We can make it infeasible for someone to attack from these vectors so that we can isolate that heterogeneous environment, which has multiple different owners, operators. We can reduce the attack surface of the OT technology and the IT technology at the same time. And we can make it simple and scalable as you go to more than 110,000 connected devices across different multiple tiers of technology, and which needs to evolve throughout its life cycle, because we know these things have very long life cycles. We don't just want to put a piece of hardware on and then have that as the single solution for the next 30, 40 years, as people were saying today. It's all about having dynamic security, all about being able to update it through the life cycle and make sure that it is relevant and secure for the future. I was in the talk earlier on, I don't know if other people were, the requiring cryptography for the future as we start to see current cryptographic methods broken. For us, because we're a software-defined solution, it's just a question of updating the endpoint to use an encryption algorithm that's crypto capable. Then obviously you need a bit more computing power at the edge to do it. But fundamentally, because it's a software-based solution, it's drop-in capability and then update through the life cycle. And that really means that we're able to solve a lot of the security implementation challenges. And that's where we then get to the, okay, we can solve security challenges, but does that solve other challenges? Does this introduce a lot of other headaches for our organization? Because there's nothing worse than saying, okay, well, this solves my security challenges, but it's 4 times the cost as my business case, or it introduces complexities on the other end that I then have to solve for those. So what we have really tried to do is to make these things as simple as possible and to resolve challenges that you traditionally have with other, alternative technologies. So obviously we were able to solve a lot of the security challenges I mentioned around. It doesn't solve all security challenges. If you've got more complex IoT devices, you should probably have some endpoint protection on them to make sure people aren't doing things. Obviously, we have to work with partners to have hardware root of trust, to have trusted boot and execution, to bring in all of these capabilities. You want to do threat management, threat detection, etc. But it starts solving a lot of the challenges that we see around the connectivity and the security of that. At the same time, because it's a fully software-based solution which can deploy onto anything, down from virtual machines to containers to a power gateway, I don't know, like a Dell 3000, 5000, or an NXP microcontroller, Raspberry Pi, you fundamentally have something that can be deployed either in the edge on a device, or if you want to go all the way down further, onto the edge environment, or if you want to go further, all the way down to a device level. And then have a consumption-based network which goes across any underlay, whether you've got mobile, whether you've got satellite, whether you've got Wi-Fi, whether you've got different internet connections into your site, and which you can then fully deliver through APIs and DevOps tools and spin it up on demand as real infrastructure as code. And then third of all, provide performance and reliability improvements than you would have traditionally against the public internet and things such as VPNs in order to enable real-time processing and to do time-sensitive data. We were a launch partner for the AWS IoT analytics for that pure reason of we need secure connectivity, it needs to be real-time. We have a customer in the US who's using us to move SCADA data from their grid environments into their cloud environment without having to have an MPLS network. And that then really gets to the point where at IoT Solution World Congress a couple of weeks ago, month and a half, we demonstrated this with a few of our partners, Micron, the leader in flash memory, Microsoft, NXP, ARM, and Tata Move with their global SIM. And fundamentally what we were demonstrating was, I've got a truck, or some sort of thing that's moving in an endpoint. I've got some sort of gateway or microcontroller on it. It's got a SIM so it can go into to any location around the globe. And then it's got the Micron Authenta chip, it's a new capability they've just developed, and they're embedding it now into all of their flash memory, which gives you hardware root of trust and a trusted boot and execution environment. And they're embedding it into all their new flash memory at no marginal extra cost. So you might as well put it there because you can have flash memory there anyway. What it allows us to do is to produce hash from the software being run in the memory, and then to produce a DICE certificate, which is an open source pushed by Microsoft certificate. It allows us to say, I know this is a trusted device because it's running the correct version of the code, and it's unspoofable because it's hardware root of trust. And therefore, we can pass that certificate over to the network controller, and it says, yeah, okay, you're allowed access to the data plane because I know you're trusted. And what we demonstrated was someone coming along with a USB stick or something, injecting malware into the endpoint, onto the flash memory. That changes the DICE certificate, and automatically the network says, you're no longer trusted. Therefore, you have no data plane access. And through the demo, you see no data coming through into your dashboards. And then you're able to go through a remediation process where you flash it back to being secure, and also supporting a heterogeneous environment by microsegmenting different things into different applications. And that really gets us to the point where now we're building those zero trust solutions with partners. We believe, yes, people do buy networks. Yes, we can sell networks, but actually people want to solve business challenges. The biggest IoT solutions we work on at the moment is things like energy management and security of endpoints. And we're working with partners to build solutions around that, because we fundamentally believe that if we sell a solution that includes our product, then that solves the customer problem rather than having to assemble their different components themselves. So we're working with the likes of Siemens and IMS Evolve, Dell, Clario, various different companies who have solutions that we can embed our software and APIs into in order to provide that secure connectivity between the edge and the cloud. So you can have secure automation-based zero trust from silicon to cloud, and which allows us to say, well, we know we're never going to be 100% secure, because you never are unless you literally shut yourself in a cupboard and you turn out all the lights and you lock it all up. We're sharing information, and therefore there's always going to be potential ways that people could get in, and there's no silver bullet. But we are able to implement a layered zero trust approach, which allows us to mitigate a lot of the security challenges that we have. And fundamentally, this then allows us to enable people that are developing IoT solutions and the developers around it to take control of their solution, to create new products, to innovate, but still incorporate security as a fundamental into their design process, so that innovation can be unleashed around IoT in the same way that innovation was unleashed when we gave developers the capability to spin up their own cloud environments and application resource environments they require to do their work. And that's very much how we're bringing zero trust into IoT. Any questions?
Thank you very much indeed.